All right, in this video, we're going to go over Unit 1, kinematics that we covered in AP Physics 1. So we began the year talking about kinematics, which really is the description of motion. And we first had to introduce this concept of vectors versus scalars. So remember that a vector is something that has both a magnitude and a direction, while scalars can be completely described by only a quantity and a unit, so only the magnitude. So really this is the number, and this is, to the left or to the right or up or at 45 degrees or whatever, right? And so the first concept of vectors versus scalars that we introduced was the difference between displacement and distance. So distance is really the ground that you have totally covered, where displacement is how far you are from where you originally began. So if you're going to drive across the country, there's lots of different routes you could take, and so the distance for every single one of those would be different. However, if you started in the same place and ended in the same place, no matter what path you would take, your displacement would be the same. Keep in mind also, for instances where we move around in circles, if you ended up back where you originally just started, then your displacement in that case is 0, right? So the rate at which you then change your position or cover some distance or displace yourself is known as either velocity or speed. So the equations really kind of look the same, but again, we're just distinguishing between which one is a vector and a scalar. Remember, whenever I say the rate at which, that's always that thing over time. So velocity would be your displacement over time. There's a little arrow here because a lot of times when you see equations, if there's an arrow, it just indicates to you that that value is a vector rather than a scalar. And over here, we have speed, which is just distance over time, right? And the units for each one of these are meters per second, because the SI unit for either distance or displacement is in meters. And so if it's the rate at which, we would have meters per second. All right. Now keep in mind that if we want to figure out the average velocity, so let's say you walked for a little bit, then you stopped, and then you ran, and then you went backwards a little bit, and then you ran forward, and then you stopped. In order to figure out the average velocity, all you have to do is take total displacement and divide it by total time, right? We want to take into consideration all those times that you were not moving or whatever, and that will give you your average velocity. Right. Now, when we say that a displacement and velocity are vectors and they have a direction, remember that a lot of times that is indicated by whether or not it is positive or negative. All right, so then if we go ahead and we take a look at the idea of graphing. So let's say we're going to graph distance in time, right? Or let's say it's position in time or displacement in time. Okay, so these are all sort of similar. Remember that I sort of use this generic D as a measurement for distance, but R is also position. Sometimes X or Y is used. Sometimes even S is used. These are all variables that are commonly used for the position of an object. All right. So let's say at first someone is just sitting there and they're not moving, they're at rest. If we were going to plot a graph that showed distance versus time, so distance on the y-axis and time on the x-axis, right? As for an object at rest, if we were to record where that person was or wherever that object is, it would be in the same position the entire time, right? Then we would have, let's say, an example where someone was going a constant velocity. So in this case, we would have the rate of change of their velocity, or the rate of change of their displacement would be the same over time. So we'd have this curve that, like, after the first second they're here, after the second here, after the third second here, and so we plot and we would see a line. Whereas if they were speeding up over time, right, or changing their velocity over time, we would see that in every second they would cover more and more ground. So in the first second they only went up a little bit, but then in the second second it was more and then more and then more. So we have these curves. So really, what does the slope of these graphs mean, right? I'm covering it up there for a second. So just remember that slope is change in y over change in x. So whatever the y rise is, if you divide it by the run, that helps you to figure out what the actual slope of that line really means. So in this case, our rise is displacement or position, and our run is time. So if we want to look at what the slope of that graph means, what is the equation distance over time? What does that mean? Meters over seconds. That is your velocity or your speed, again, if this is distance and not displacement. All right, so then let's go ahead and take a look at what it means when we are changing our velocity over time. All right, so here we can see that the slope the entire time is equal to 0. So that makes sense because you are at rest, right? So you're going 0 meters per second. Whereas here you have some constant positive velocity, whereas here it's changing. So if we're going to take the slope at any point in this graph, it would be the line tangent to the curve, right? And so then we could just sort of follow along and we could see that the slope of that line tangent is getting bigger and bigger and bigger. So what do we call that? So your change in your velocity over time is actually your acceleration, right? And you can accelerate or change your velocity 3 different ways. Now, the most intuitive way, and the one you're probably most familiar with, is the idea of speeding up, right? So we can change your velocity by going faster, right? However, less intuitive is that acceleration can also mean slowing down. But because velocity also has a direction, you can also accelerate by turning. So even if you maintain the same speed, you can turn and then we'll have some form of acceleration. So acceleration is your change in velocity over time, or your rate of change of velocity. So the equation that we have is the change in velocity over time, which change in velocity is v final minus v initial all over time. And the unit then we have for that is meters per second or meters per second squared. So then if we're going to look at those same graphs, the at rest, going a constant velocity, and accelerating or a changing velocity. But now let's look at it in terms of velocity in time rather than position in time. So this is what our graphs would look like. If you're at rest, then the velocity that you're going at every second would be equal to 0, right? Over here, we see that we're going a constant velocity, so the velocity is some value, but it stays the same the whole time. And then over here, we see that the if you're accelerating, you're going faster and faster and faster, so you would plot a greater velocity in every second. And again, this is just an example of speeding up, but remember, we also have this idea of slowing down too. All right, so anything that does not have a slope is not going to have an acceleration. So when you're at rest or when you're at a constant velocity, anything with a slope means that you're accelerating, right? Versus when we look at those other graphs, if we have a curve, so let me just pop back to them. Remember, for displacement versus time or distance versus time graphs, anything linear is going a constant velocity, anything curved is then accelerating. Right? So the slope of the position versus time, the slope of the velocity versus time graph actually will give you the acceleration because we have rise, which would be our v over t, which is what our equation for acceleration is. Now, also, as we covered this, these graphs, we looked at a new concept of area under the curve. So really, our curves in AP Physics 1 are going to be either rectangles or triangles, but the area under the curve for this example is going to be equal to a rectangle. In order to find this area, you're going to multiply y times x, right? And in this case, that would be velocity times time, which actually would give you the displacement because of a result of this. So we can see here, like just visually, the displacement of the object using the velocity versus time graphs, right? So lastly, I want to talk about some examples where we have constant acceleration. And so the most common example that we use really is this idea of gravity. And remember, this is acceleration due to gravity. And it is always acting downwards. And the value for it is -10 meters per second squared. All right. Now we use the negative when we're doing, when we started here with these constant acceleration equations, but then later when we start talking about forces, remember we let our free body diagram indicate the direction of this. All right, so we did also then derive two constant acceleration equations that allow us to calculate any other variable. So we have the velocity final squared is equal to the velocity initial squared plus 2 times a times d. And remember that this really is our conservation of energy equation, where we have 1/2 mv squared equals mgh. So where this is g and this is h, and then if I go over here, if I move this over here, it would be v squared over 2. All right, so that really is the same as our conservation of energy equation. And then lastly, the other equation that we had was that d equals v initial t plus 1/2 at squared. Right? So this equation doesn't have time in it. This equation doesn't have v final, so no time, no v final. And then our other equation where we have v final minus v initial all over t, this has no displacement in it. So really given any variables, we could solve for any constant acceleration problem. So one of the most common examples that we use is throwing a ball up in the air or dropping something. So just to remind you of some little tricks about when we drop something, if a person is up on the top of a cliff or whatever and they drop something, just some things to remember is that at the start of a drop, the v initial is equal to 0 meters per second. So quite often you'll be using this equation and you'll be using just this part, so d equals 1/2 at squared. Sorry, that got kind of sloppy. And then also, if we're going to toss something up in the air, there are some things to conceptually remember about this sort of example. So up at the top, we know that the object is going to stop for a minute. So the velocity up here at the top would be 0 meters per second. We also know that the time to fly up in the air would be equivalent to the time that it takes to fly down in the air. And we also know that because the acceleration is equivalent, the velocity initial is actually going to be equal in quantity or in magnitude to the velocity final. However, this one would be going up and this one would be going down. And direction really is important in this instance. One last thing that I just want to take a look at before I end this video overviewing all of Unit 1 is the idea of graphing acceleration versus time. Now, we haven't really done this, but we can look at this pretty easily when we have our certain instances, right? So we can just kind of apply our other ideas of, that we've been using acceleration versus time. All right, so if an object is undergoing a constant acceleration, right, then we're going to have some line like this, whereas if an object is undergoing no acceleration, we would have a graph like this. Right? But again, you probably won't go too into detail about this, but just knowing some very basics about acceleration versus time, or even being able to understand what they mean, would be helpful, right? I guess since I've got one more minute before I can end this video, let me just look at one more thing too. So we've used the idea of gravity, right? Acceleration due to gravity being negative 10 meters per second squared. So if we were going to plot the velocity versus time graph for an object that is accelerating due to gravity, then we would expect to have a slope like this, where the slope of this line would be equal to negative 10 meters per second squared. All right, so hopefully this covers all of Unit 1 in just 15 minutes.